Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. When we look at a point in a three-dimensional space, we can describe the point as having an x, y, z coordinate in the Cartesian or rectangular coordinate system. When the geometry of our 3D shape is of a cylindrical nature, there's another system of coordinates which simplifies the solving of problems when, say, we have to integrate to find the volume of such objects. This system is called, you've guessed it, cylindrical coordinates. The system extends polar coordinates in 2 dimensions and adds a height component z. So for this tutorial, I'll assume you've watched the video I made on polar coordinates, as much of what we covered is relevant to cylindrical coordinates. If you've not yet watched it, have no fear, I'll drop a link to it in the description. So let's suppose we have a point in a 3D space. In Cartesian coordinates, we could describe the location of the point as having an x, y and z coordinate, where z is the height component. If we draw a line from the point to the xy plane, we see that the distance from the point to the xy plane is equal to z and is the z coordinate. And then, if we draw a line from the origin to the point on the xy plane, this distance, as we saw when looking at polar coordinates, is known as the radial distance r. And the angle it makes with a positive x-axis we can call theta. Theta rotates in a counter-clockwise direction from the positive x-axis. In cylindrical coordinates, z remains as z. The x and y coordinates are converted to an r, theta coordinate in an identical way to what we saw with polar coordinates. So let's quickly recap on how r and theta are calculated. Using this diagram, we're looking down from the z-axis onto the xy plane, and we can use a combination of Pythagoras' theorem and basic trigonometry to convert the x and y coordinate to an r and a theta coordinate. If we look at the diagram, we have a right angle triangle where x is the horizontal displacement from the origin and y is the vertical displacement from the origin. The radial distance r is the hypotenuse of the triangle. So we can use Pythagoras' theorem to work out r. And so r squared is equal to x squared plus y squared. And r is equal to plus or minus the square root of x squared plus y squared. Note here we have a positive and negative r value. The negative r value indicates a radial distance in the opposite direction to the positive r value. So if the positive r value is shown by the red line, the green line indicates its negative value. For the purpose of this tutorial, we'll be using the positive r value. And for the angle theta, we can use basic trigonometry, where the tan of theta is equal to the opposite side of the triangle divided by the adjacent side. This equates to y divided by x. And so theta is equal to tan to the minus 1 of y divided by x. Now we need to take care when calculating theta and make some adjustments based on which quadrant we are dealing with. Once again, see the tutorial on polar coordinates for more in-depth information on this. And as noted in the introduction, the height component z does not change when converting from Cartesian coordinates to cylindrical coordinates. If we now want to convert back from cylindrical coordinates to Cartesian coordinates, we can use the same triangle to do so. So on the triangle, we can see that the cosine of theta is equal to the adjacent side divided by the hypotenuse side. And this equates to x divided by r. And so solving this equation for x, we have x is equal to r cos theta. And similarly, the sine of theta is equal to the opposite side divided by the hypotenuse, which is equal to y divided by r. And solving this equation for y gives y is equal to r sine theta. And once again, the height component z remains the same. Let's now look at an example where we convert a point in Cartesian coordinates to its equivalent in cylindrical coordinates. So we're going from x, y and z to r, theta and z. Our point in Cartesian coordinates is 2, minus 2 and 4. So x is equal to 2, y is equal to minus 2 and z is equal to 4. And I've marked this point on the diagram. And so to find r, we're going to take the positive square root of x squared plus y squared. So if we plug in the numbers for x and y, we have r is equal to the square root of 4 plus 4. And therefore r is equal to 2 multiplied by the square root of 2. And theta is equal to tan to the minus 1 of y divided by x. And so theta is equal to tan to the minus 1 of minus 2 divided by 2. And therefore theta is equal to minus pi by 4 radians. And now to get the positive counterclockwise angle of theta, we need to check which quadrant it lies in on the xy plane. And so we can see it lies here in the fourth quadrant on the xy plane. And therefore we can adjust it by adding 2 pi. This will then give us a counterclockwise angle from the positive x-axis. So when we do this, we see that theta is equal to 7 pi by 4. So now you can see that I've marked the angle in, which is 7 pi by 4, and the green line denotes the radial distance r, which in this case is 2 root 2. And as for z, this remains as z equals 4. So Cartesian coordinate 2 minus 2 and 4 converts to 2 root 2, 7 pi by 4 and 4 in cylindrical coordinates. So now let's convert a point from cylindrical coordinates to Cartesian coordinates. So that's from r theta z to x, y, z. So the point in cylindrical coordinates that we're going to look at is r equals 3, theta equals minus pi by 3, and z equals 2. So to get the x coordinate, we know that x is equal to r cos theta. So x is equal to 3 cos minus pi by 3, which is equal to 3 over 2. And for the y coordinate, we know that y is equal to r sine theta. So y is equal to 3 sine of minus pi by 3. And that equals minus 3 root 3 divided by 2. And we know that z remains unchanged, so z is equal to 2. So I've drawn the point in on the diagram. So we have an x coordinate of 3 over 2, a y coordinate of minus 3 root 3 over 2, and a z coordinate of 2. So 3 minus pi by 3 and 2 in cylindrical coordinates converts to 3 over 2 minus 3 root 3 over 2 and 2 in Cartesian coordinates. And in our final example, let's convert an equation from Cartesian coordinates to cylindrical coordinates. So the equation we have is z equals the square root of x squared plus y squared. And as you can see, this is the equation of a cone. The cone is centered at the origin and is formed above the xy plane. To convert this to cylindrical coordinates, we need to replace all the x values with r cos theta and all the y values with r sine theta. And after we make this substitution, we get z equals the square root of r squared into the bracket of cos squared theta plus sine squared theta. And using the trig substitution where cos squared theta plus sine squared theta is equal to 1, we're left with z equals the square root of r squared. And taking the positive square root, we're left with the equation in cylindrical form where z is equal to r.